and we can solve the integral.
Okay.
In other words, if I go back up here to this integral, and I substitute for q bar 7.5, now the problem becomes easy. Right?
Right. Okay. That makes sense.
And you know how to evaluate that? First of all, what's the integral of 15 minus 2q?
15x squared over 2.
Actually, just be 15q. The integral of
15q minus 2q squared over 2.
Right, which is that. Right. Minus 2q squared over 2, the 2's cancel. So here's my integral, and I'm going to evaluate it between 0 and 7.5. So I've got 15 times 7.5 minus 7.5 squared minus 0, because when I substitute 0 for both of these, I get 0. Okay. So whatever this number is your answer.
Okay.
Okay. The only difficulty was really finding q bar, and we had to use this that I'm pointing at over here. The d of q bar is equal to p bar, and they told us p bar was 3, so we just had to figure out what q bar was.
Right.
And we did that. Okay. What else you got?
Let's see. Here, I just got a screenshot. I'll send you.
Okay. I have a hard time running everything that needs to run while GoToMeeting is running. GoToMeeting really is a processing hog. It needs a lot of computer power.
Yeah, no kidding.
I frequently, during the middle of a session, will get a notice that you need to turn your camera off. We're running low on resources. So.
All right, there we go. I just sent a screenshot of a graph.
Okay. Okay, so when t is 0, that's 2004. Oh, that's not right there. It's somewhere over here. But I guess it's there. This graph doesn't quite look right, but I'll figure it out here. Okay. Compute s prime of t. Well, that should be easy enough. If s of t is 15t squared minus 76t plus 101, what is s prime of t?
I'm sick. All right, so that's 30t minus 76.
Okay. And what is S prime of 3?
90 minus 76, which is 14.
Okay, and then what else do they ask here? According to the model, Facebook memberships (2007). So it looks like this 2-year period, that would be true.
Okay. All right, that wasn't too difficult. Just wanted to go over that quickly.
Yeah. Yeah, the only part of that at all that's any trouble is part B. And that, what they're basically saying is that the slope of the tangent line at 3 is less than the slope of the tangent line at 4, and that's certainly true. If you were to draw a tangent line there, the slope is increasing. So the memberships are increasing at a faster and faster rate, meaning the slope of the tangent line is increasing.
One sec, got another screenshot here.
Okay. Boy, it was hot on the golf course, but my phone was in my pocket the whole time, and it wasn't until I got in the car and drove for 40 minutes that my phone overheated. It was really weird, yeah. I've never had my phone do that before.
It happened pretty often to me in Arizona.
I'll bet. Okay, this is what I thought your consumer demand was going to be doing yesterday. This is marginal cost, which means the cost of producing the next item. In other words, if you produce X teddy bears per day, what would the cost of producing the next teddy bear after that be? Well, it's the derivative, so what's the derivative of that function?
Let's see. That would be 0.0. That would be 45 minus 0.18x.
45 minus 0.18x. So what's the, when they say how fast is the cost of production level of, is the cost going up at a production level of 100 teddy bears, which is basically saying what is C prime of 100?
Okay, which would be 45 minus 18, which is
27. Okay.
27.
Compare this with the exact cost of producing the 101st teddy bear. Well, if everything I said is true, exact cost of producing the 101st teddy bear. Well, let me think about this a second. It seems to me that if we figure out the cost of producing 100 teddy bears, and then figure out the cost of producing 101 teddy bears, and subtract those two costs, that'll be the exact cost of producing the 101st teddy bear.
Okay.
So let's do that. So C of 100, now this is not C prime, this is C of 100, is going to be 100 plus 4,500 minus, oh my goodness, 0.09 times that, which is 900. So we have 100 plus 4,500 minus 900, which is 46 minus 9, 3,700. So that's the cost of producing 100 teddy bears. Now what is C of 101?
Uh,
100 plus 45 times 101 minus 0.09 times 101 squared. I'll let you do the arithmetic here.
so that's 100 plus 45 times 101 minus 0.09 times 101 squared. 3726.91.
So the exact cost of producing the 101st teddy bear must be this number minus this number.
So 2691?
Uh-huh.
All right.
So our answer to this was what again? It was 27. It was 45 minus 18. So the cost is going up at $27 per bear at 100 teddy bear production rate. So that's pretty close. 26.91 is awful close to 27. So that makes a lot of sense.
It does, yeah.
Okay, so the exact cost of producing, we did that. I think we've done this, haven't we, fully? The average cost function, this is something else that I don't have the formula for. You either need to send that to me or tell me what it is.
One sec.
Problem is calculus can be used in all kinds of disciplines. Most of the calculus that I do is just straight math, so we don't always get these formulas for economics and stuff. Do you have something similar to what you sent me before that gives what C bar of x is?
Perhaps.
I'm guessing it's probably an integral of some kind.
Speaking of integrals, we can move on to something else and come back to this.
Okay.
Well, I've spent a lot of time working on integrals because I struggle with those.
Okay. Integration is an awful lot harder to do than differentiation.
Yeah,
With differentiation, we have product rule, power rule, quotient rule, and chain rule, and between those four rules, I can differentiate any function you want to give me. Integration, not so. In fact, I can give you a function that there is no antiderivative for, right there. There's no way to find an antiderivative for that.
Right.
You have to use very sophisticated techniques of infinite series and infinite sums in order to evaluate this.
All right, but let's start out with the first integral they give us. It's the integral of, in parentheses, 2x minus 3 quantity squared.
Okay. This is fairly straightforward. Let's just expand it. In other words, we know that the integral of sums and differences is the same as the sums of those integrals. So when you square this, you get now it's easy to take the integral up.
Okay, yeah, so that would just be 4x cubed over 3 minus 12x squared over 2 plus 9x.
Plus c if it was an indefinite integral.
Right. Okay, well that was pretty easy.
Yeah.
So let's move on to the next one then. Okay,
Okay.
push this one in real quick.
Have you had integration by substitution and integration by parts?
Yep.
Okay. That's probably the only two techniques you've worked with, is my guess.
Yeah.
Because there's lots of others. There's integration by partial fractions. There's integration by trig substitution. There's more techniques than you can shake a stick at.
All right, the next is the integral of 7e to the x over 4. As in the exponent is x over 4.
Okay, what's the integral of e to the x?
E to the x?
What's the integral of e to the 2x? E to the 2x divided by the derivative of the top. So it would be e to the 2x divided by 2.
Okay.
Okay, so this fits that category. So this is going to be 7e to the x over 4 divided by 1/4, or multiplied by 4.
Okay.
Okay. Same way that the integral of sine of 5x is negative cosine of 5x divided by 5, divided by the derivative of the inside. So your transcendental functions, the e to the x and trig functions, you can find the antiderivatives pretty much with the power rule, or variation of the power rule, I guess.
Makes sense.
Yeah.
All right, the next integral.
Plus c, I mean, it's real easy to get in the habit of not putting that plus c down there. I don't know if when you're taking a test that'll ever come into play, but
All right, next integral is, 1 sec, it's loading.
Okay.
Okay, it's in parentheses x plus 1, close parentheses, e to the, once again in parentheses, x plus 1 squared. And it says to solve it using substitution, and with the u being
X plus
x
1.
plus 1 squared.
With the u being x plus 1 squared?
Yes.
Okay. Okay, so if, what is du dx? Let's see, because this is dx. Okay, so if we're going to solve it by integration, we're going to need a du. Because basically, what I'm going to do is I'm going to substitute u, square root of u for that. And then I'm going to have e to the u. And then I still have dx, so I have to replace this dx with a du. So I have to solve for du. I have to do the differential equation to solve for du. So let's go to this. Du dx would be equal to what? How do you take the derivative of that?
2 times x plus 1
To the first power. And so that's 2x plus 2 is du dx, which makes du equal to 2x plus 2 dx, which makes dx du divided by 2x plus 2.
Okay.
So instead of dx, I have to put this in there. So now I can write this thing as the square root of u, e to the u, and instead of dx, I'm going to put all of that. Du over 2x plus 2. Okay. Now, in order to get rid of the x, in other words, when you're using substitution, you want the final integral to have nothing but u's in it. You can't handle an x because we're not doing dx, we're doing du. So right now this is not very convenient because I got this 2x plus 2 down there. Well, if I go back and resubstitute, I really didn't need to put square root of u there. I could have left it as x plus 1 for the moment. I'll hold it. It was just x plus 1. And it's still e to the u du over, and let's factor out an x plus or a 2. So I've got that. So now that cancels with that, and I'm down to my final integral, which is nothing but u's. I can take the 1/2 outside the integral. So I've got e to the u du. You see how I got to that step?
Yeah, I see what you did.
Okay. So now it's easy to do. That's 1/2 e to the u, and go back in and substitute x plus 1 squared plus c. Now, actually, I just remembered, I did this probably, didn't need to quite do it the way I did it. I'll bet you in your class you do it this way. You've got du equals 2 times x plus 2 dx. Okay, well, if I look back at my original integral, I'm looking at that. There's the x plus 1, there's the dx. So if I find that, I can substitute du for it. Well, in reality, it's x plus 1 times 2. So what I would really want to do here, let's go back to this step right here. I want to take a half out and put a 2 in, like that. That's usually what calculus suggests you do. Okay? So now I see that I have 2 times x plus 1 and a dx right there. Well, that's exactly what I have right there. 2 times x plus 1 and a dx. So I can substitute that and that with a du and do it that way rather than the original way I did it, which maybe is a little more helpful for understanding what you're doing, but it's an extra step to do it the original way I did it. And most courses will try to get you to recognize that in the original integral you already have a 2x plus 2 and a dx. And that's what I got over here, so I just do a straight substitution of du for that. And I end up actually getting this right away.
Okay.
Okay? I'm glad they said integrate that by substitution, because I would have been tempted to try parts. Because usually if you have a polynomial times a transcendental function, that's when you want to use integration by parts. But in that particular case, substitution actually worked perfect because everything was just right. You know, if it had been a 2x plus 3, it wouldn't have been perfect.
All right, well, the next one, another integral, once again, it says decide on what substitution to use.
Okay.
It's 7.2 root of negative 4x plus 5 dx.
So what do you figure we should use for u?
The negative 4x plus 5?
Yeah, because then what we'll have is 7.2, which I can actually take outside the integral. Let's do that immediately. And I'll end up with the square root of u, and I know that I can integrate this. Okay, so that's why I want to use u is whatever is inside of there. So let's let u equal negative 4x plus 5. So what is du dx equal to?
Sick. Just 4?
Negative 4.
Negative 4.
Which makes du equal to negative 4 dx. So actually in this case, since I don't see a negative 4 anywhere up there, I'm going to use my first technique, which is to solve for dx, which in this case, dx is equal to du over negative 4, right?
Right.
So now I'm going to rewrite the integral, taking the 7.2 out there. I've got square root of u, and in place of dx, I'm going to write du over negative 4. Now I can actually take the negative 4 outside the integral. Now I'm dealing with just that.
Okay, 1 sec. So that's okay.
So I'll leave that there. What's the integral of u to the 1/2? Use just the power rule.
Oh, right. So it's just the
Add 1.
u to the 3/2 over 3/2, right?
Right. And the power rule is, that's always the way I do it. I just always just add 1 to the exponent and divide by the new exponent. Okay? So this now becomes, let's see, I'm going to multiply by 2/3. So I got 2/3 times a negative 7.2 over 4 times u to the 3/2. Go back, resubstitute for u. So I got negative 7.2 over 6, and u was once again minus 4x, what was the rest of it?
Sorry.
Plus 5.
Yep.
To the 3/2 plus c.
Just real quick, when you did the 2/3, you were that was just taking the integral.
No,
Oh,
in other words, we were dividing by 3/2, which is the same as
Oh.
multiplying by 2/3.
Oh, okay. All
I
right.
flipped it and multiplied. Did you by chance have a chance to look at our recorded session yesterday at all?
No, I haven't yet. I'm going to spend most of tomorrow just watching these over so I can...
I was going to say, it'll probably be more helpful to you than it will be most of my students. In other words, if we were practicing for the SAT, it wouldn't be all that valuable to you. But
Right.
when you're covering material that you're not 100% clear on, it should be pretty valuable to you.
1 second. I'm just going to go grab my laptop charger real quick.
Okay? It's the only problem with technology. Batteries can lose their juice and computers can overheat, I guess.
Yeah. Well, nothing's perfect.
No, really. Sure does beat the alternative, though, huh? Meeting in a library somewhere in between and having to struggle with all of that.
Yeah, that would not be fun.
No. I know. I did that for the first couple of years I was tutoring, and it wasn't fun. Actually, I lived in Colorado Springs, and most of my students were in Denver, so I really had difficulties. It's one of the reasons I really pressed developing my online tutoring capability.
Yeah, this is awesome.
Yeah.
How this all works. And I take it you do this year-round whenever people need help?
I do. I usually don't get that much work in the summer, but this summer's different. I've got calculus students coming out of the woodworks this summer.
Huh. Okay, so if I were to contact you in Arizona, we could do a session there as well?
For sure. Absolutely.
All right, awesome.
Yeah.
They got, those big tutoring centers, but, they can only spend so much time on one person at a time before they got to help someone else.
Right, right. Now, are you in your, are you starting your first year at ASU, or you're starting your second year?
I'll be starting my second year.
I know somebody at ASU. What the heck is her name? Cole. Kristen Cole? You know Kristen?
Doesn't really ring a bell.
Probably like asking somebody, oh, I know somebody in New York City. Do you know them?
Yeah.
There's a lot of people at ASU.
Oh, yeah, to say the least.
You have a math professor at ASU that won a poker tournament online I was watching a couple of years ago.
Really?
Yeah, I don't remember his name, but he played against, I don't know if you're a poker player or not, but he was at a table with Phil Hellmuth, and he did real well. He won like $50,000. Yeah.
Oh, wow. Huh.
Yeah, he was not a poker pro either. He was just a math professor at ASU that got on this program.
I'm going to have to look up that program then. Huh. All right. The next integral is 6x square root of negative x squared plus 4.
Okay. How are we going to do this?
Should we substitute again?
Yeah, this is perfect for substitution. So what's du dx?
Negative 2x.
So if I'm searching for that there, what do I need to do? I need to change this 6x into minus 2x.
Take out a 3 then? A negative 3?
Take out a negative 3 and put in a negative 3. So now I have minus 3. I put in a negative 1/3 is what I put in. Okay. So now I've got minus 2x square root of u dx, and this combined with that is equal to du. So now I've got square root of u du, and I have an integral that I can integrate.
Okay.
Okay, so this becomes minus 3 u to the 3 halves multiplied by 2/3, which is equal to minus 2 times minus x squared plus 4 to the 3 halves plus c. Hold it. Yeah, no, I did that right. Yeah.
Okay.
And I think it's worth noting that you can do these either way. I'm not that convinced that I like this way. Even though this way saves a step, I almost prefer solving for dx and just in place of dx writing du divided by minus 2x and then dealing with the negative 3 that you get on your own.
Just real quick, how did you go when we had the negative 3 times u to the 3 halves? Where does the Yes, there. Where does the 2/3 come into play?
Okay, so we got negative 3 u to the 3/2 divided by 3/2.
Okay, so that was just
So
taking the
again, we
integral?
flipped that and multiplied by 2/3 instead of dividing by 3/2.
Okay, so wait, just so that the 3/2 on the bottom, where did that come from?
That came from when I integrated u to the 1/2.
Oh, okay.
This was u to
Okay.
the 1/2, so I added 1 and then divide by the new exponent, which gave me 2/3 u to the 3/2 times the minus 3. And of course, one way you can always tell, if you're never sure you have the right answer, then let's integrate, or let's differentiate this. This is fairly easy to differentiate. Becomes, I take this exponent, multiply it by the minus 2, so I get minus 3 minus x squared plus 4 to the 1/2 times the derivative of the inside, which is minus 2x. So that should be what I started with. And it is, because we started with 6x. Minus 3 times the minus 2x gives us 6x times the square root of minus x squared plus 4.
Okay.
That's always the case. If you're not sure that you've integrated it properly, just take the derivative of what you have, and you need to get back to the function you started with.
Okay. That makes sense. All right, then. So our next integral, it is x to the 5th minus x to the 4th all over 5x to the 6th minus 6x to the 5th dx.
Well, let's do what we can do, which is what? Let's apply some factoring here and see if we can winnow these x's down.
Okay. So we just want to take out the largest power of x we can.
Yeah, we can do that, I guess. Let's see. If I take out x to the 4th, I'm left with x minus 1. If I take out an x to the 5th, I'm left with 5x minus 6. And then I can cancel that with that exponent, like that.
Okay. Where do we go from there?
Yeah, I'm thinking.
Okay.
Let's see, if I put them back together again, I get this. Okay. I'll leave them factored like that. Let's use u substitution.
Okay.
This is going to work a little different than most u substitution works. If u is equal to x minus 1, well, first of all, what's du equal to?
dx.
Okay. Now notice that I can actually solve for x. If u is equal to x minus 1, then x is equal to u plus 1.
Huh.
So does that help? Let's see what we got. We got u over u plus 1 times 5 times, I don't like what's happening here. Why not? Let's see. This might work after all. 5 times u plus 1 minus 6 is the same as u minus 1. So now I've got the integral of u. Notice that multiply those two together, you get the difference of squares. Now this actually fits when you're doing integration by substitution. What you really want is the tough part to integrate. You want its derivative to be on the other side of the fraction line. And notice that the derivative of the bottom is 2u. Let's use substitution again.
Okay.
Only this time I'm going to let t equal u squared minus 1. So what is dt? du?
2u.
So dt is 2u times du. So now I have the integral of u over t, and I need to substitute for du, which is dt over 2u. Because the derivative of the inside was u, it gets rid of that, and now I merely have a function of t that I can integrate. Now, did I need to go through double substitution? Probably not. If I go back to the original problem, yeah, notice that if I take, in other words, I don't need to go through all of this. Let's start this problem again.
Okay.
Notice what the derivative of the bottom is. Notice that that is in the top, minus the 30, but it's easy to handle numbers. So I'm going to make, starting from the get-go, I'm going to say u is equal to 5x to the 6th minus 6x to the 5th. Because then du dx is equal to 30x to the 5th minus 30x to the 4th. And I've got that in my numerator, minus the 30. Let me put a 30 right there and a 1/30th out there.
Okay.
So now I have du equals 30x to the 5th minus 30x to the 4th dx. And this whole thing I see right there. It's the numerator of my integral. So I can substitute the entire numerator with du. So I immediately go, whoops, excuse me, where am I at here? I immediately go to this step, and I've got du over u. See how I get that?
Mm-hmm.
In other words, I just let u be the denominator, noticing, in other words, what you want to notice when you're doing substitution is if one side of the fraction's derivative equals the other side of the fraction. Or it doesn't even have to equal it, as long as it's a constant factor of the other side. Well, the bottom side of this expression was 5x to the 6th minus 6x to the 5th. And I notice that the derivative of this is this, x to the 5th minus x to the 4th, all times 30, but that's fine. I can handle the 30 easily.
Mm-hmm.
Now I have in the numerator 30 times x to the 5th minus x to the 4th dx. Well, that whole thing is equal to du right there. So I just substitute du for it. And then the bottom is u. So I end up with an integral that's this, which is very easy to do. What's the integral of 1 over u?
That's the same as
Natural log of u. This is the one integral. Notice that this is not, you can't use the power rule on this. What happens if I try to use the power rule on that?
you get something over 0.
Exactly. So this is the only exponent where you can't really apply the power rule. You just have to know that the integral of 1 over u is natural log of u. It's actually the natural log of the absolute value of u.
Okay.
So our final answer is going to be 1/30th natural log absolute value of 5x to the 6th minus 6x to the 5th plus c.
Okay.
In fact, I've tutored calculus courses that don't even call that using integration by substitution. They just call that using integration by the power rule.
Huh.
In other words, they've kind of incorporated the fact that you're looking for the composite function to use the power rule. Okay, what else? So when you're, I guess what I'm trying to say is when you're looking for what to let u equal, take the derivative of what you're considering and see what it looks like. Well, the derivative of that happened to look very nice. It came out 30x to the fifth minus 30x to the fourth. Notice that if the derivative would have come out to be this, I got big problems. I can no longer do this thing.
Right.
But as long as it had 30, that means I can factor out the 30, and I'm left with what I had in my numerator.
Right.
And that's the key. You're looking for that exact expression or a constant of that. You have any integration by parts, or have you heard of the lipid?
I have not.
You have an integration by parts problem?
Yes, I do. I have one right here.
Let's do it.
6x e to the negative x.
Okay, dx. This is the integration of a product. But we don't have a product rule. But we kind of do. What our product rule for integration says is that the limit of u dv is equal to u times v minus the integral of voodoo. So here's our primary formula we're going to use for parts. So our first step is to figure out what to let u equal and what to let dv equal. And that's where lipid comes in. You go in the order of this. In other words, if there's a log expression, let that equal u. If there's no log but there's an inverse trig, let that equal u. The last priority, if there's a polynomial, let that equal u. So this has no log, no inverse trig, has a polynomial in it. That's what I'm going to let u equal. And what do you let dv equal? Everything else. This is where calculus starts becoming kind of confusing, because this is a lot different than substitution. In other words, we're letting u equal something, and then we're letting dv equal something that has another differential in it also. And the reason we do is notice that to solve for this, I need u, I need v, and I need du. Well, I can get all of those things. I've got u, but I don't have v, and I don't have du. But I can solve for du by differentiating the u part. And I can solve for v by integrating the dv part. And that's always what you want to do. And in fact, I would recommend that you set it up like this, where you put the u on the left, you put the dv on the right, and you're always going to be differentiating the u, the left part, and integrating the right part. You're going to find that integration is as much differentiation as anything. It's hard to integrate without doing some differentiation also.
Right.
Okay? So now I got everything I need to plug into this.
Okay.
So what is u?
6x.
What is v?
E to the negative x. Or negative e to the negative x.
Minus the integral of what is v du.
Negative e to the negative x times 60x.
Okay? That's an integral we can do. Notice that I can remove the 6 and I can integrate that real easily. So I've been able to take an integral that I couldn't do and turn it into an integral that I can do.
Okay.
Okay? You want to, let's go through the rest of that. Hi, come here. Hi. Shh. So my final answer is going to be, let's put the e to the, I'll 6 minus 6x, e to the minus x, that's u times v, minus, well, let's see, what is this integral? If I take, first of all, if I take the minus outside, it becomes plus, and now I'm just integrating, I can take the 6 out also. So what's the integral of e to the minus x?
Is it still e to the minus x?
Divided by minus 1, turning this back into a negative. When you're doing integration by parts, the hardest thing is keeping track of your negative signs, because also integration by parts frequently requires multiple iterations. If you start this problem off with 6x squared instead of 6x, then after the first iteration, I'm going to have a similar looking integral, only I will have knocked the power of x down by 1. And then I have to do the whole process over again until I knock the power of x out of there completely. And I'm going to knock it down by 1 each step. In other words, if this started out 6x to the 5th, I got to do 5 iterations to solve the problem. In this case, since it was 6x to the 1 power, 1 iteration is all I needed to get rid of that polynomial of x and end up with something that I could integrate, which is just e to whatever. E to the minus x is easily integrated.
Okay.
Have you had the tabular method for integration by parts?
I have not. Do you want to use that on our next example?
Well, let's see what the example is. Maybe we can use it, maybe we won't.
In parentheses, 2 minus x, close parentheses, e to the x.
No, this will just be a straight. Okay, let's have you do this one. What's u going to be?
2 minus x?
What's dv going to be?
E to the x?
E to the x dx.
Right.
Okay, so what's du?
Uh, 2 minus x dx?
Okay, what's du dx?
Negative 1.
Okay, which makes du equal to minus dx.
Oh, okay.
Okay? In other words, you can treat them like fractions, even though they're not really. They're differentials, but you can do what we just did. In other words, if du over dx is equal to minus 1, then du is equal to minus dx. Okay, so now we have our u, we have our du, and we have our dv. What's v? We need v. Get that by integrating the right side. The integral of e to the x is e to the x.
Right.
Okay, so now using what we know about u, v, and du, let's plug in. What's u times v?
2 minus x e to the x.
minus the integral of v du
which would be e to the x minus dx.
Let's take that negative sign out, making that positive. And then what's the answer? What is that?
E to the x.
Okay. Yeah, it's just e to the x. So we're not quite done. You don't want to give it in this form. And if you're dealing with multiple choices, this probably won't be your choice. What can we do to that expression?
Simplify it?
Factor out an e to the x.
Oh, okay.
You almost always are going to be able to factor something out. And I'm not quite sure why they do it, as opposed to leaving it in an expression. I guess because it does simplify a little easier.
All right. That makes sense.
Yeah.
You said you were available tomorrow after 10?
What's tomorrow? I'm playing golf tomorrow at 11:30. And I have a 9 to 10. I could see you for an hour from 10 to 11. Just barely. I need to leave here by 11. Or I could see you later in the day. I could see you after. I'm probably going to get back here at about 5.
Okay, could we do a session later tomorrow evening then?
Sure. You want to do that?
Okay, then I think we can wrap up for today.
Okay, let me pull up my scheduler here.
Okay.
And tell me. Yeah, so this is what my tomorrow looks like. Let's see, 11:24 plus 4.5 hours is 4 o'clock. I'd be back probably by 5, although I kind of hate to be on such a tight schedule. 5 would probably work, but 5:30 probably gives me a little more leeway, or 6.
Okay, would you, yeah, we can,
You can pick, 5:30 or 6, either one.
5:30, just we tend to eat around 6:30, but 5:30 would work well.
Okay, let me put you in. That'll be online at 5:30. And are we going to do that for an hour? It doesn't really matter. I don't have anything after that. I'll go ahead and block off an hour and a half. You can take whatever of it you want. So today we actually went from 3:15 to 4:25. Sound right?
Yep.
Okay. I will text you. I'll put my phone right in front of the air conditioning unit in my car if I have to. I will text you tomorrow right about 5:30.
Okay, awesome. Thank you very much.
Okay, Robert. I'll talk to you tomorrow.
See you then. Okay,
Bye-bye.
bye-bye.